Curious, when you look up at the night sky, it is easy to assume you are seeing the whole picture. For most of human history, we believed that the glowing stars, the rocky planets, and the swirling clouds of cosmic gas made up the entirety of the universe. This chart shows the actual mathematical breakdown of our cosmos. All the atoms in all the stars, planets, and people you have ever known account for barely 5% of reality. Roughly 27% is dark matter, and the remaining 68% is dark energy. The vast majority of our universe is made of materials that do not emit, reflect, or absorb light. We are entirely blind to 95% of the cosmos. Our understanding of this unseen reality began with the discovery of cosmic expansion. In the 1920s, Edwin Hubble proved that galaxies are steadily moving away from one another. Then, in the 1970s, astronomer Vera Rubin found an anomaly. This graph plots how fast stars orbit based on their distance from a galaxy's center. Based on the visible mass, stars at the outer edges should orbit slowly, shown by the downward curve. Instead, Rubin observed a flat line. The outer stars were moving just as fast as the inner ones. At those extreme speeds, a galaxy should instantly tear itself apart and fling its stars into deep space. To stay intact, it must be held together by an immense amount of unseen mass, a massive, invisible halo of gravitational glue. We call this unseen mass dark matter. The visible galaxies we can see are actually secondary structures caught within a much larger, invisible framework. If dark matter is a gravitational glue holding structures together, its collective pull across the universe should act like a brake. Logically, the expansion Edwin Hubble discovered should be slowing down over time as all this mass pulls inward. In 1998, astronomers tested this logic by observing distant Type A supernovae, specific exploding stars that have a known, predictable brightness, acting as cosmic mile markers. Examining the light from these blasts, researchers found the supernovae were significantly dimmer and therefore farther away than the deceleration theory allowed. Independent teams of astronomers scrutinized the math, trying to find an error. They verified the exact same anomaly. The light had been stretched far more than expected. The expansion of the universe is not slowing down, it is speeding up. To drive this acceleration, physics demands the existence of a repulsive cosmic pressure, actively pushing the fabric of space apart. This is dark energy, and it accounts for the final 68% of reality. Dark matter and dark energy serve entirely opposing mechanical functions. Dark matter acts as cosmic scaffolding. It counts together, creating intense gravitational wells that draw in regular hydrogen gas to build stars and galaxies. Dark energy operates differently. This diagram represents the fabric of empty space. Dark energy is an intrinsic property of that space. It does not clump, it acts smoothly and uniformly everywhere, pushing outward. This creates a mechanical paradox. As the universe expands, matter spreads out, and its gravitational pull dilutes. But as new space comes into existence, more dark energy appears along with it. This leaves the universe in a state where its expansive force is increasing, while its gravitational anchors are growing weaker. These two forces have influenced cosmic structure since the Big Bang. In the early universe, matter was packed tightly enough that dark matter's gravitational pull dictated the evolution of stars and galaxies. But as the universe physically grew, the matter thinned out. About 5 billion years ago, the density dropped low enough that dark energy's repulsive effect became the dominant influence on the expansion rate. Because dark energy's strength scales with empty space, the acceleration will continue to compound. In the deep future, the space between galaxy clusters will expand faster than the speed of light, pushing our cosmic neighbors beyond our horizon. Cosmologists project this will lead to a scenario known as the Big Freeze or the Big Rip. The night sky will be swept completely clean of light and heat, leaving isolated galaxies to slowly burn out alone in an icy, expanding void. The atoms making up our bodies, our planet, and our star are largely irrelevant to cosmic mechanics. The unseen 95% of the universe will ultimately dictate how everything ends. Today, physicists are trying to identify the exact particles responsible for these effects. A leading theory suggests dark matter consists of weakly interacting massive particles, or WIMPs, heavy, slow-moving fragments from the Big Bang that pass right through regular matter. To detect a WIMP colliding with a standard atom, researchers build particle traps deep underground, utilizing miles of solid rock to filter out background cosmic radiation. Simultaneously, engineers are assembling massive new space telescopes to map the distribution of matter in the early universe, measuring how dark energy has influenced the growth of structures over billions of years. By pairing underground particle detection with high-resolution space surveys, we are shifting from merely inferring these forces to measuring them directly. Quantifying this 95% of the cosmos is the next step in establishing a complete model of physical reality.